Welcome to Hot Chips 29. Session 3, Automotive.
Good afternoon. I'm Forrest Basket, and I'm introducing people for our automotive session, perhaps more accurately called our autonomous automotive session. The first speaker is Mitsuhiko Igarashi, who received his degrees in physical electronics from Tokyo Institute of Technology in 2005 and 2007. In 2007, he joined the Technology Development Unit of Renesas Technology Corporation, where he worked on researching and developing low-power circuits and designs. In 2010, he transferred to Renesas Electronics Corporation, and he now works on research and development of reliability solutions with aging sensors for automotive SoCs. And he's going to tell us about R-Car Gen 3. A computing platform for autonomous driving era.
Thank you very much for your kind introduction. Today, I'd like to talk about our solutions towards the autonomous driving and also talk about our approach towards the LSI challenging for autonomous driving. So let me start with the overview of my presentation. First of all, I'd like to introduce our ADAS autonomous driving platform called Renesas Autonomy. Then, I'd like to briefly describe the challenging for autonomous driving and our solution to it. After that, I also demonstrate the Level 4 autonomous driving concept car. Finally, I'd like to introduce the concept of reality management for future autonomous driving usage. Then, I'll finish with a brief conclusion. So let me introduce our autonomous driving solution called Renesas Autonomy. As you know, there are several applications in autonomous driving, such as sensing, judging, and of course, vehicle control. And connectivity to the cloud service is much more important for future automotive. So in order to meet these demands, we provide end-to-end solution called Renesas Autonomy. For not only for vehicle control MCU, but also sensing, judging, and connectivity solution. So we'd like to contribute to the next autonomous driving society. So this slide shows the difference between each level, autonomous driving levels, and our solution. So as you can see, the requirement of the future is different between each levels. So higher level requires much more sensor, functionality, and performance. So it means optimal solution towards each level is different. So we provide a scalable solution for sensing and connectivity solution with compatibility. So next is we'd like to describe the challenging for autonomous driving and our approach to it. So as you know, we need much more performance to realize highly or fully automated driving. So of course, we are pushing hard to increase the performance, including deep learning performance and so on. However, we think it's not enough for the automotive and mass production class. It is because we have to realize the performance with low power. It is because huge power consumption leads to the consume of the car's battery, and of course, there needs expensive, huge cooling system in a limited space of the car's ECU unit. Second is functional safety mechanism to avoid the car's accident. It is because, as you know, so car's accidents directly influence the impact on the human life. So we need functional safety. high reliability is also required for the automotive as the same reason. So in this way, we have to achieve also high performance, but we should be safety first in automotive. From the next slide, I'd like to introduce our solution to overcome these challenges in our SOC. So this slide shows our solution for energy efficiency. In automotive LSI and autonomous driving, there are several kinds of tasks such as video processing, replanning, and so on. So each characteristic is very different. So in order to improve the energy efficiency, we allocate each task to the suitable automotive ratings, such as image recognition engine, and so on. Also, we apply the several parameter tests to improve the energy efficiency as a basic technology. So the other important point is real-time operation, which is strongly demanded on the automotive. So in automotive, several kinds of tasks is running at the same time in parallel. So it may cause stack transaction when main task is running at the same time. So in order to prevent the stack transaction of the key IP bus access, we developed the parallel processing preferred bus network architecture. From the next slide, I'd like to describe more about the power management techniques. So this slide shows a diagram of power management techniques for the low power. We apply the power gating techniques and has 21 power gating domains, including each cluster shutdown for the GPU to thoroughly reduce the leakage power. We also apply the dynamic voltage scaling techniques and adaptive voltage scaling to CPU and GPU to improve the energy efficiency. In addition to these techniques, we also develop function safety areas, reliability areas, power management techniques. So I'd like to introduce from the next slide. As you know, voltage drop is one of the key factors to restrict the performance and energy efficiency. And this voltage drop has a large time-scale events, such as very fast AC voltage drop to the slow DC voltage difference between the chips. So in order to detect and manage it, we implement several kinds of on-chip monitor. And one of important drop monitor is Droop monitor. This can detect and predict the fast AC voltage drop. By using this monitor and clock control techniques, we can prevent the functional failure caused by excessive voltage drop. So it is because, roughly speaking, if excessive voltage is predicted by this monitor, we access the clock controller to reduce the operation frequency in order to reduce the power, so result in recovery of the voltage drop. So I'd like to introduce the measurement result of this monitor in the next slide. Left-hand side means the measurement condition, and right side means the measured result. The sampling rate is 67 picoseconds to detect the AC voltage, fast AC voltage drop. As shown in the right side graph, vertical axis means the voltage course, and horizontal axis means the time. And small voltage course means low voltage condition. That means bottom side of this graph means there is a big voltage drop. And dotted line means measured result without prediction techniques, and solid line means the predicted one. So as you can see, there is almost the same result. So we can successfully predict the AC voltage drop. In addition to these techniques, we also implement the mechanism to run BIST in a field called runtime test. This can enable to detect the functional failure caused by wear out. So in this way, we can predict and detect the functional failure caused by each failure mode. So let's move on to the reality-aware Droop mitigation techniques. Metal insulator metal capacitance called MIM capacitance is generally used to reduce the voltage drop. So increase of the, roughly speaking, increase of the capacitance between the ground line and power line would lead to reduce the voltage drop. So in other words, increase of the capacitance lead to be reduce voltage drop. However, there are some challenges in automotive because to satisfy the automotive reality grade, such as ESD and wear out failure rate is a ppm level. So we implement the dedicated ESD circuit to be a HC200 capable. The HC200 is the standard of the reality for automotive SI. As for the wear out failure, mean capacitance also causes wear out failure, and its failure rate is depending on its usage area. It means increase of the mean capacitance leads to increase the wear out failure rate. So in order to satisfy the required ppm level wear out failure of the automotive, we optimize the mean capacitance usage between the CPU and GPU region. As a result, we achieve 60 millivolt improvement of the voltage drop. We have to reduce not only for wear out failure rate, but also early failure rate. So as shown in the right side graph, mean capacitance failure mode is to be short between metal and metal of the mean capacitance and causes a short current. So therefore, we should detect this short current as a time of testing to detect, prevent the early failure of the mean capacitance. However, in conventional IDT tests, it is generally used. It's hard to detect this short current because, generally speaking, leakage current of the CPU and GPU, etc., has larger leakage than the short current of the mid failure. So in order to overcome this problem, we introduced a minimum IDTQ test to emphasize this short current by suppressing leakage current. In this way, we developed safety-aware and reliability-aware power management techniques for automotive reliability requirement. The next session, I'd like to demonstrate the Level 4 autonomous driving concept car and its feature. This is the system diagram of demo cars. One of the key focus is fail operation. As you can see, we use 4 Alka-3 chips and 2 P1HC chips. And P1HC is the automotive grade MCU. One of 4 H3 is used for sensor vision processing and detection of the lane, stop signal, stop light, and so on. The other 3 of H3 is used for sensor fusion, lane planning with triple redundancy. So in this way, we realize a redundant system by using triple redundant H3 usage. As for the power consumption, we only consume 25 watts despite we use triple redundant H3 usage. As already mentioned, one of the main focus is fail operation. So we decide the lane planning by majority decision of the 3 Alka-3's result. So it does not cause malfunction of the car, even if one of 3 Alka-3 is failed. Moreover, S3D compliant MCU can detect this failure, and system automatically drives the car to the safety zone by using remaining 2 Alka-3. So in this way, we can realize fail operation by using this kind of redundant usage. So let's move on to the next topics. It's a concept for reality management for future autonomous driving usage. We think there are 2 different ways in future automotive. One is owner-driven car, which is a conventional way, and the other is mobility service car, which is a new wave. In owner-driven cars, autonomous driving technology can support the driver and can address the reduction of the car accident increase of driving pressure, and so on. On the other hand, in mobility service car, the important value for the user is different from the owner-driven car in the conventional direction, such as service pressure, mobility service, cloud service, and so on. So landscape for the user value is changed in future automotive. In addition to that, connected car with the cloud would be much more increase much more. In that case, much more data, various kinds of data will be collected through the data. It means car would be a sensor node. Consider this case, it is expected that several kinds of services provided based on this several kinds of data. And we think one of the important services is vehicle quality enhancement for service car. So in that case, we think the demand for the information of the LSI reality and demand for the LSI reality enhancement itself is one of the important points in the future. So let's take a look at the car usage change in future automotive. Currently, according to the HC200, operation rate is less than 10% we expected. On the other hand, in fully or highly automotive driving era, it is expected to be dramatically increased in future autonomous driving era. It is because both autonomous driving technology and the paradigm shift of the car usage, such as mobility service car. So in order to fill in this gap, we think the further reality enhancement of the LSI will be one of the key challenges for future autonomous driving era. So then, how to improve the LSI's reality more? Let's take a look at the trade-off between reality enhancement and the performance. This figure shows the voltage and temperature dependency of both reality lifetime and performance. As you know, reality lifetime is strongly depending on the voltage and temperature, and also have the variation as well as the process variation. So therefore, we can opportunity to extend the lifetime by controlling this parameter in some way. However, if we simply apply the low voltage and low temperature control, it causes performance degradation. So we need smart voltage and temperature control mechanism to extend the lifetime without performance degradation. So in this way, we propose a concept of reality management for future LSI further reality enhancement of the LSI. So unfortunately, time is limiting. So I'd like to briefly introduce the outline of this reality power management techniques. There is several kinds of the reality items, and one of the key items is bias temperature stability and hot carrier injection, called BTI and HCI respectively. And this element causes power bank degradation called aging. So our concept is a two-step. One is a static control at the time of testing, shown in this slide. And the other is dynamic control in a field, shown in the latter slide. We use on-chip lifetime odometer called LTO. This monitor can detect the BTI and HCI degradation chip by chip to detect its variation. By using this aging variation information, we extend the lifetime without performance degradation. So generally speaking, in conventional way, we added the constant voltage guard band in the operation voltage to prevent the delay failure caused by aging. In our reality management techniques, we optimize this voltage guard band depending on not only for voltage setting and process variation, but also aging variation. This can enable to extend the lifetime without performance degradation and negligible yield loss. So let's move on to the dynamic control. First is the voltage control. So we predict the lifetime by using on-chip monitors such as lifetime monitor and voltage and thermal sensor. So if predicted lifetime is closer to the EOL setting, we overdrive the chips which does not reach the upper limit of the voltage. That means this chip has room to increase the voltage in terms of reliability. By increasing the voltage, so we can extend the lifetime because performance has room. Performance is boosted. Next is adaptive voltage thermal control techniques. So as shown in the right side graph, the power consumption is depends on the process variation. It is because, as you know, leakage power is strongly depending on the process variation. So it means some chip has causes a low junction temperature, even if the same environments, same task. So in order to ensure this low voltage operation, we adaptively control the threshold of the thermal control depending on its electrolyte characteristic. So briefly speaking, in summary, we smartly control the voltage and temperature depending on each characteristic, and also use aging variation of each chip. As a result, we expected 5.6 times lifetime in total, and at the worst case, is expected without performance degradation. It's realized around 50% operation rate. So we think these kind of techniques should be a solution to overcome the upcoming dramatic increase of the autonomous driving error. So I'd like to briefly introduce the summary. I introduced a total solution for autonomous driving computing platform called Renesas Autonomy. We also described the challenges for autonomous driving and our solution. We also demonstrate the concept car for level 4 autonomous driving, and its feature is low power with failed operation. I briefly introduce the concept of reality management for future autonomous driving usage. In this way, Renesas would like to contribute to the progress of autonomous driving technology to enhance not only for performance, but also energy efficiency, functional safety, and reliability. That's all I have to say. Thank you very much for your attention.
So we have time for a couple of questions. Let's see, we have one over here. Would you just say your name and then the question?
My name is Tadao Nakamura, Cool Chips Conference Series. Okay, you compared your chips with NVIDIA chips.
Yes.
And you mentioned the power consumption of both.
Yeah.
And I wonder whether or not your chips performs all the functions of NVIDIA's chip. What do you think?
Okay, that's a good question. And I think, of course, performance is different between our chip and NVIDIA chip because they use DGPU. Yeah. So I think performance is different. So it might be not an apple-to-apple comparison, but in addition to that, we also continue to develop this concept car. It will have much more performance, much functionality, and it will be soon be available, maybe next year or so. So it's a tough question, but it's just example for the comparison.
Okay, I understand.
Thank you for your question.
So I have one more question for you. You've got lots of reliability and failure mode contributions here, but what is the overall target for these systems that you build? Is it
Target?
years?
It's a tough question to answer the actual target. Easy because
years?
generally speaking, around 50 years or more is required for the tier 1 or OEM or so on. So, of course, it depends on the requirement and application. But the trend is the required lifetime is increased because autonomous driving should be much more safety. So I think much more reliability and will be required in future automotive.
So you think these cars will be more reliable than the cars we have today?
So yes, we should be more reliable.
Well, thank you very much.
Thank you very much.
So the next talk is by Fergus Noble. Fergus is a co-founder and CTO of Swift Navigation, where he is focused on building the technology that will enable autonomous vehicles to navigate and understand the world. At Swift, he spearheads R&D, technology strategy, and architecture. Prior to Swift, he obtained his BA and MSc degrees in physics from Cambridge University, where he worked on GPS for high-altitude rockets. He moved from the UK to California to work for Joby Energy on GPS systems and flight software before co-founding Swift in 2012. His talk is Localization for the Next Generation of Autonomous Vehicles. Fergus?
Thanks, Fergus, for the introduction. Autonomy is arriving, obviously in the form of self-driving cars, but we're increasingly seeing more and more automation with drones and in agriculture. And fundamentally, autonomous vehicles need to perform two tasks. They need to do obstacle detection, see what's around them, and avoid crashing into anything. And they need to know where they are in the world so that they can navigate. Other than using a sextant, GPS is basically the only way we have to know our absolute location, our latitude and our longitude on Earth. But it's inaccurate. GPS today that you have in your cell phone or your car is accurate to about 15 feet or 3 meters. So to enable these new autonomous applications, we need an advanced centimeter-accurate GPS-based localization system. Autonomous vehicles today have 5 key sensors. We've got radar, which is used for that obstacle detection feature. And then we have vision, so cameras basically, and LiDAR, 3D laser scanning. They're primarily used for obstacle detection, but they're also used for localization. You build a map of what's around you, you find features in it, and that can be used to identify where you are in the world. And then we obviously have GPS and inertial sensors. So with vision and LiDAR, these are optical-based systems. They have a certain set of limitations. So if in situations, because they're based on features, in situations where you don't have any features, such as a desert road, where everything looks the same, or if you have some snow on the ground or insufficient lane markings, these systems are going to have a very hard time. So we need to complement them with other sensors to provide a robust solution. As we heard in the previous talk, the automotive industry has defined different levels of automation, 5 different levels, starting from level 0, which is no automation at all. Level 1 is the cruise control you're familiar with, you've had for a long time in your vehicle. Level 2 is basically where we are now as an industry. Level 2 systems are able to control both the steering and the throttle of the vehicle, but the primary responsibility for safety is still with the driver. As we move on to level 3 systems, this is where we get to a truly automated driving system, where the primary responsibility for safety starts to move over to the vehicle. These systems may still only operate in very limited scenarios, but we're starting to move that safety responsibility to the vehicle itself. And that's a big leap that we have to make as an industry. And then level 4 and 5 progress to wider and wider situations in which you can drive until you can just put in your address and go. But bridging this gap from where we are today with level 2 to level 3 is going to require a large leap in the robustness and the safety of our systems, requiring better sensors. So what do we need for autonomy? Obviously, we need high precision. GPS today isn't sufficiently accurate to distinguish which lane we're actually in, which can make it obviously a huge difference as to what you're going to do next as a driver. We need availability. I mentioned all different sensors have scenarios in which they're not going to be able to give you a position. For GPS, you're not going to get any signal inside of a tunnel, but as soon as you get out of that tunnel, you need to have that system available again. It's not good enough to wait another 10 minutes for your GPS to turn back on. We need integrity. Integrity means being able to trust in the output and not get any misleading information. So we've all had the situation where we're driving along the freeway and our GPS is telling us we're on the overpass or we're on the frontage road. That's an inconvenience when you're driving, but when your car's driving you, that's going to be a very significant problem. And we need to do all of this for a low cost so that this can be built into essentially a consumer product, a vehicle. So these are some of the requirements. Let's talk now about how does GPS work and what are some of the limitations of the standard techniques that we're going to have to overcome. So with GPS, we're positioning based on satellites. We have a constellation of 30-odd satellites, 20,000 miles overhead, and imagine we can measure the distance from that satellite. Knowing the distance from one satellite puts us somewhere on the surface of a sphere. If we add a second satellite, we know we're somewhere where those two distance measurements are consistent with one another. We must be somewhere where those two spheres intersect. You can see how this is going to go. If we add a third satellite, our location must be somewhere where all three of those distance measurements are consistent with one another. That gives 2 points. One of those is going to be on the surface of the Earth, and the other is going to be miles off in space. So in practice, that uniquely determines our position. And if you've worked with GPS, you might be thinking, well, hey, usually I need 4 satellites to get a position, and that's because of time. We've locked down a 3 degrees of freedom, latitude, longitude, height, but as we're going to see, we need time to actually do these distance calculations, and that's why we need a 4th satellite. So hopefully this shows with some simple geometry, if we can make distance measurements from the satellites, then we can determine our position. So how do we actually go about measuring these distances to the satellites? We obviously don't have a direct measure. We don't have a huge 20,000 mile long tape measure, so we've got to use some indirect measure of distance. And for that, we use time of flight of a signal. So if you imagine a satellite transmits a pulse at time 0, we pick it up some time later, we can multiply that time of flight by the speed of light and get an approximation to the distance. Now, these satellites are extremely far away, and they're transmitting with a power of about 400 watts, so the power of a bright light bulb. The signal that we receive on Earth is 20 decibels below the thermal noise floor of the receiver. That is to say, if you were to look at the signal coming into the antenna, you would see just pure noise. So we have to use a lot of sophisticated signal processing techniques to boost that signal up out of the noise and make it readable. So let's look at some of the limitations that limit the accuracy we're able to achieve with these systems. There's just a ton of different errors that affect the GPS signal. So just to give you a flavor of this, we have effects such as the sun's radiation hitting the top of the atmosphere. This is called the ionosphere, and it disrupts the propagation of radio waves as they go through. We have what we call the troposphere. This is water vapor in the atmosphere, weather, very unpredictable effect that delays the signal going through. We have perturbations to the orbits of the satellites. We have small errors in the atomic clocks they have on board. We have environmental effects, reflections from buildings, and so on. We need to take into account each of these errors in turn, model them, and offset them in order to go from the 3-meter precision we're familiar with today to the centimeter accuracy that we require. So just to give a flavor of how we are able to eliminate some of those errors, at Swift, we use a technique called real-time kinematics. It's not a very descriptive name, but it basically has two essential features. It's differential, and we'll go into what that means in a second, and the second feature is that it takes advantage of carrier phase information from the satellites. So starting with differential, this isn't a very good diagram, but imagine you, instead of having one receiver with your user, you have two receivers, and one you designate as a base station, just an identical receiver to what the user has. And say they were spaced maybe 10 or 20 miles apart. Now remember, these satellites are at 20,000 miles altitude, so this actually forms a very long, thin triangle, such that as the signal propagates from the satellite down to those two receivers, they basically pass through the ionosphere at the same point. This means if you take the measurements from the two different receivers and just subtract one from the other, which is where the differential part comes in, you have some part that's in common that is affected by that ionospheric effect, and then you have some difference left over, which is unaffected by the ionospheric effect. And now, when we were looking at the geometry earlier, we needed the full distances, but what we have now is this little difference measurement. So we have to think of a way, how can we take this difference measurement and from it estimate something about our position? And it turns out there's a fairly simple way to do this. So again, imagine the satellite is so far away that the signals are basically coming in parallel to one another. If we think of the vector between the two receivers, the baseline vector, we call it B, forming a right-angled triangle with the line of sight to the satellite, that little difference measurement is just equal to what you would get if you projected that baseline vector onto the line of sight. So that if we have enough measurements enough of these difference measurements, we can do a solution and actually obtain the baseline vector. And this shows why this is fundamentally a relative positioning technique, because we have a very precise measurement of the offset between these two stations, and we need to know the stations of the coordinates of the base station in order to get the coordinates of the user. The other problem we have is just the inherent measurement precision. I mentioned, we're sending this data signal, which is used to get timing information from the satellite. That signal has got a data rate of about a megahertz, so each bit is a microsecond long. At the speed of light, that corresponds to 300 meters per bit. We can measure the timing from this signal to about 1% of the bit width, so that gives us an inherent precision of only about 3 meters. The carrier that's used to transmit that data has a much shorter wavelength of about 20 centimeters. So if we can actually make a measurement of that carrier, measuring the actual wavelengths of the radio wave used to transmit the signal, we can get a much more precise measurement. The trouble with the carrier is, though, that every single cycle looks the same as the last one. We can measure the fractional part of the phase, but we have no way to know how many whole cycles there are between us and the satellite. This is called the integer ambiguity problem, and we call the solution integer ambiguity resolution. And this is really the fundamental difficulty of doing any of these precise GPS techniques. So we have this unknown parameter called the integer ambiguity, which we want to estimate. And in engineering, we have a fabulous technique that allows us to estimate unknown parameters called a Kalman filter. The trouble with the Kalman filter, like many other similar techniques, is it's not really able to deal with the fact that we know this quantity is an integer. That's an extremely powerful constraint. So we need to augment the Kalman filter with a method which will take advantage of the integer nature of this parameter. So if you imagine the range of all possible values that this integer could take for example, two different satellites, we could say N1 is the integer ambiguity for satellite 1, N2 is the integer ambiguity for satellite 2. The different possible values of that integer ambiguity would be points on a grid. So we know that the true value is one of these grid points. But using our Kalman filter estimator, that's not, that estimate we obtain is not going to be locked. It's not going to be snapped to one of those grid points. The great thing about a Kalman filter, though, is it does give us a confidence interval. It gives us an ellipse, and it says, all the points inside this ellipse are much more likely to be the true value than all of the ones outside. So we need to take this initial estimate and find what is the grid point that is closest to that estimate, but taking into account this ellipse. So, for example, in this diagram, you can see there's a point that's very close that's outside the ellipse and some that look much further away, which are inside the ellipse. The ones inside the ellipse are actually more likely than the ones outside. So the physics of the problem results in these ellipses for this GPS problem being extremely elongated and thin because the integer ambiguity is highly correlated between the different satellites. So, for example, you might have a range of 10 different integers possible for each of the different satellites, and if you think of the volume bounded by this space, you might have 8 different satellites you're receiving from simultaneously. There would be 10 to the 8 different grid points, different candidate points that you might care to look at. And naively, the only way you have to know of whether these points are inside the ellipse or not is to test them. So you're stuck with this situation where you would have to enumerate 10 to the 8 different points and do a test on them. It's just computationally intractable. However, there is a trick. There is a technique called lambda, which basically squishes that ellipse into a circle and makes the bounding box much, much smaller. It's easy to find a transformation that will squash an ellipse into a circle, but in general, that transformation is not going to preserve the integer nature of those points. What starts out as an integer on the left, after it's transformed, will not necessarily end up being an integer. So the lambda transformation finds the optimal transformation that turns the ellipse into a circle whilst as close to a circle as possible whilst keeping that integer nature and makes a much smaller bounding box. So then from that, we're able to enumerate all of those points, find which one is closest to our initial estimate, substitute that back in, and get an ultra-precise measurement of the distance to the satellite from which we can derive centimeter-accurate positioning. So at Swift, we've incorporated this into our product Pixie Multi. This is a credit card-sized module that's able to position to centimeter accuracy within a matter of seconds. And we're able to do this for about 1/10 the cost of any competitor. We sell these today for $600. We've also taken that technology and in our new product, Duro, wrapped them in a durable enclosure that's waterproof and suitable for really harsh environments. So this is perfect to just strap on the top of a vehicle and go driving, or deploy into harsh outdoor environments, agricultural, marine, and other industrial applications. So just to end on a note about why this is important. 38,300 is the number of automotive-related fatalities we had in the United States in 2015. Worldwide, that number is over 1 million. That corresponds to a fatality every 25 seconds. Self-driving technology is the best opportunity we have to reduce this number, and I believe that we can get this number to 0. Thank you.
Oh, that was great, Fergus. I will just reiterate one point that he made very quickly is you can buy these units online for $600 today. Some of you might find that interesting. So questions? Do we have questions for Fergus? This is, I think, I'll point out that 2 centimeters is about half the size of a lane marker. Question over here?
Yes, John Masuris, Lucky Unity.
You mentioned that you're doing differential GPS, so do you have to buy at least 2 of these cards to get the centimeter accuracy? And what's the power dissipation per card?
Yeah, so each module runs about 3 watts right now. And today we sell them as kits of 2, like you say, so you can deploy one, for example, in an agricultural scenario, you might put it on your farm and be able to serve a radius around that.
Thank you.
You might stay tuned on that front, John. There could be some really interesting news coming down the road.
Hey, Fabian, Cooper GmbH, and I'm wondering if you're looking into using geostationary satellites to use as the base station.
Yeah, the base stations currently do have to be situated on the Earth because they're actually, we call them a base station, but really what they are is a GPS error monitoring station. So they're sampling for us what are the contributions of all the different GPS errors at that point on Earth. So you want them to be on the ground where basically they're experiencing the same errors as the user. That said, there are opportunities to potentially use geostationary satellites to transmit those corrections to the users or distribute the data.
But it's not implemented right now as it is, right?
Not today. We use an internet backhaul. Any kind of internet connection is suitable for distributing the corrections today.
Thanks.
So how many base stations would you need to cover the Bay Area?
These stations can be very sparse. That's a good question. When we talk about this, people think about building the next cell network with thousands of stations. You could cover the Bay Area with less than a dozen stations, maybe 6 or 8 stations.
One more? Go ahead.
Hi, Eric Quiddle from Samsung. I was going to ask more about the lambda part. You sort of went very quickly through. You're translating from an ellipse to a circle. I imagine that you want that to be lossless, but I don't know whether that truly is, and you're putting dots in there. I'm coming from the computer architecture world where, the famous Intel FDiv bug, there's charts like that where you're making pretty lines around circles and you're trying to make approximations of integers. I'm curious if there's some catastrophic corner case where sometimes you do this translation, a dot sort of falls on the line, and what do you do? Does it just sample again, or is lambda truly lossless?
Yeah, those are some great questions. If the dot falls on the line, so that is a corner case we have to take into account. That really happens if the ellipse is effectively so thin it's just a straight line. So we have to handle those cases separately. Is it lossless? In a sense, it is. I mean, it's just a transformation. You get a different representation of the same data on the output as you had on the input. And to give you a little bit more of a sense of how it actually works, the algorithm finds a step that will take an ellipse and make it very slightly more circular whilst preserving the integer nature. And then it just iterates on that procedure until you can prove that it will descend to a kind of an optimal point.
But if you get a corner case like that, it's not a catastrophic failure.
It is not a catastrophic failure.
Okay.
Yep.
Okay, well, thank you, Fergus. That was terrific.